Perfect. So good afternoon, ladies and gentlemen. My name is Chris McCool. I'm a professor at the University of Bonn. I lead the Agricultural Robotics and Engineering group. Today I'm going to present some work that we've been doing, or that I have also been a part of, for robotic vision and action in agriculture. Today we're really going to emphasize some of the work that we do around robotic vision so we can understand the environment that we're working in. You can see on the bottom of the front page there the website for my group. Today, I'm going to give you, just to outline the talk, I'm going to give you a brief motivation for doing some of this work, particularly within precision agriculture, and what I mean by that and what I hope we get to build up to. I'm then going to give you a very brief outline of some of the robotic vision data that we deal with and why we approach it in that particular way. And then I'm going to show you two applications. So one of the themes that you're going to see throughout this presentation is that we're developing systems that use similar data for different applications, like in glasshouses or horticulture or arable farming, but it's similar underlying idea and belief behind it in terms of the systems that are built and deployed there. And then I'm going to give a quick summary and we'll take some questions right at the end. Now, why are we looking at robotics in agriculture? Hopefully I don't need to tell you, but it's sometimes good to have a little bit of a background impression as to why these kind of things are important. It's because we've done extremely well at improving the amount of food we make in a limited amount of area. We've gone from hand tools through mechanization, through having different technologies in terms of chemistry, and then in precision agriculture developed to actually improve the way that we produce our food. And one of the most recent trends has been around precision agriculture. And it's worth noting how some of these precision agriculture systems work in practice. So we think about precision agriculture as it kind of stands today. You can kind of think about this particular map, where you can see on the left-hand side, we've got an image taken of a field. And, we think there's something going on with a field where we might want to do some site-specific application. And often what's meant by site-specific application is we look at, okay, we've got a particularly hot area that needs more input of fertilizer than others, as indicated by this map on the left, and we're going to divide it up into 5 by 5 meter chunks, 25 square meter area, to go through and then do precise application of fertilizer. Now, in my mind, that doesn't really bring about the really precise application that I think of when I think about robotics. When I think about robotics, I think more like the precise application of doing really precise, for instance, in terms of weed management, precise application of a mechanical tool only when necessary. And you see that example, hopefully, on that video on the right-hand side, where we go through, we find the different plants in the field, and we deal with them on an individual basis, rather than doing the broadcast, applying everything to the same area, or in the case of precision agriculture, providing the same action for a 5 by 5 meter area. Really trying to build up so we can do individual plant management. Now, I've been lucky enough to be involved with a few projects. This is kind of some of the background work that I did when I was working in agricultural robotics back in Australia with Queensland University of Technology, just to give you a bit of a background of some of the other work that I've done beforehand. In the top left, you can see there's a robot called AgBot2 that was going through the field, trying to classify the different plants within the field to do detection and classification, and then do an interaction based on that classification using a mechanical tool. If you have a system like that, some of the ideas that we're thinking about deploying were things like, can we do a summarization or a scouting of the field? And you can see that in the top right video. We'll talk a little bit more about that in detail today, where you're trying to summarize what's in the field without knowing a priori what kind of plants you actually have in the field. Some of the other work related to horticulture is this idea on the bottom left-hand side of 3D move to see, so trying to move around occlusions based on multiple viewpoints and to integrate that information so you can move, for instance, an arm around particular obstacles only by estimating how much of the crop you see. And on the bottom right, we'll talk about this one as well in a little bit more detail, looking and going through and building up systems that allow us to do the estimation of the number of fruit in a field and also the ripeness estimation, so if it's green or red, but we'll go into a bit more detail about that shortly. Now, all of these systems rely on robotic vision, okay? All of these systems require robotic vision systems to make sense of the environment that they're operating in. And why do we use vision? Well, we use vision regularly, it allows us to work in an unstructured environment. If we had an environment like in the top right, where we had a whole bunch of shelves moving around, we could record their position, this would be much more structured. And in fact, there are robots that do car assembly, and they work in a really structured environment. For us to cope with an unstructured environment, we need to understand what's actually going on. And vision allows us to see things that are both close and far. Cameras are now ubiquitous and lightweight, especially with Zoom. We definitely have more people in this particular meeting. We have more cameras in this particular meeting than we have people, because I'm sure everyone also has a mobile phone. So they now also come with batteries, with processing. So cameras are a really obvious way to try and deploy these particular systems, these robots in the field. And advances in machine learning and AI have allowed us to be able to interpret the environment. But don't let any of the statements I just told you before fool you into thinking that this is a simple and a solved problem. And hopefully you can see this picture with sufficient resolution that you can see it's a challenging problem. What you see here is a sweet pepper field, and you see field-grown sweet pepper where you've got green leaves with the green crop in the background. And normally when we're in presence, I'd be asking all of you to give me a vote on how many sweet pepper you think is actually in the image and where they are. Because this is a challenging problem, even for people to solve. And this is sometimes a problem that we're posing to our robots to really understand the environment in which they're deployed. Final answer, of course, is that there's actually 6, and they're here. So if you see one of my later presentations, unfortunately, you'll know the answer. But it's a really challenging problem. Over here, you can only just see it within the background, whereas these 2 are more prominent. But we can still use these images to make sense of the environment. What we do in my group is we go through and actually use 2 particular modalities quite often to try and solve this problem. And this video shows you what we use within our group primarily. What you see here is RGBD data. You've got the color image on the left and the depth data on the right. And also I've shown you a video sequence because quite literally many of our systems are deployed such that we're trying to exploit the temporal information in some way so we can actually deploy a system in a challenging environment, like for instance, the glasshouse environment that you see here. Hopefully, if you start looking at the image on the left as it goes through, what you're going to see is that as you see the crop appear at different times, entering from the right-hand side, you're also going to see that as we go through, some crop which were occluded before become unoccluded. And so it makes it easier to actually see and to track and to tell us that there is actually a crop within that image. And we're able to exploit the depth information on the right-hand side, and I'll show you some of the simple ways that we exploited depth to improve our systems within this particular environment. Now, just to really emphasize that point, I'm just going to skip ahead a little bit to this video, and now you should see as the crop appears up here on the top left, you'll start to see what I mean as we change the viewpoint with our system as it goes through the field. That sweet pepper up here, hopefully you can see my mouse, was becoming much less occluded by the leaf at the top as we went through getting those different viewpoints. And so what you can do with a system like that is start to make some very simple assumptions about the environment that you're deploying your particular robot in. And we're deploying our robot in an agricultural environment. And so there's some assumptions we can make. We can basically say that the scene is relatively static. And if we assume that our robot is not moving very quickly, then detected objects should remain viewable for a certain period of time. And I've tried to illustrate that idea over here on the left-hand side. Sorry, on the right-hand side over here. And so what you see over here is that you've got the orange frame, the information from the previous time step. You've got the segmentation in orange here of the different sweet pepper, these 2 here, from our previous viewpoint. And we're assuming at our new viewpoint, given by the blue or cyan image, there's going to be significant overlap between those 2 images. And you can use that very simple underlying structure within the environment to build up a really nice tracking system where what you can do is have a nice detection system running. And if you assume that each detection is overlapping sufficiently, it's the same object, you can go through and count the fruit quite effectively. And so you see that here in this particular video. What you're going to see in this video is that we're going to be detecting objects using a faster RCNN system. We're going to actually then have a subcategory, a hierarchical classifier. So it says sweet pepper, and then it says it's either green if it's green, orange if it's mixed color, and red if it's red. And this is the ripeness estimation. But please keep in your mind that this is a hierarchical kind of classification that's going on. We do detect sweet pepper and then classify the subclasses. And what you see in this video is just a handheld camera going through using the very simple assumption that I mentioned before to count the number of fruit and to estimate their quality within the field. So you know what kind or how many fruit you've got for harvesting, so you can deploy your workforce to deal with that and to harvest the fruit in the time required. And it goes on and shows that this kind of system works in different conditions, different lighting conditions. As long as you're not moving too fast, as long as there's sufficient overlap, the system will also still work. But if you're going to deploy the system on a robot, like the one you see here, so this is PadoBot, you design things a little bit differently so you can actually deploy it for challenging situations in glass houses where you've got crop that's potentially 2.5 meters high. And so what we did here was we developed PadoBot and actually had it so we had a repeated set of camera systems so we could cover the whole viewable area. So we could cover the 2.5 meters. So we can do things like automate tasks such as you see the person here with a phenotyping, trying to estimate what's going on by just touching the leaf to try and estimate the state of that leaf and that plant. And so what you can do is you can take this system and go through, it's not completely automated, but it's mostly automated. It'll go through and now detect the start and end point, go through, collect all this data so you can do some really interesting things with it. Because now we're not just capturing data with a camera, we're capturing with a robot. So now we have odometry information. And so this idea is being shown here where you can take the detections and actually filter out the background detections. So we're not detecting in the rows behind us, but also then take the detections from the current frames and reproject them. I'll explain that very shortly, but basically it's taking the fact that you've got detections from one frame and you can predict where it should be in the next frame. I'll unpack that very shortly. So you can go through and then do this so you can do much better counting of the fruit by taking into account the structure of the environment that you're dealing with. You know that you're going to be surveying the closest row. You can then also use this to start building up really interesting 3D models. This is a very simple, almost naive 3D visualization. We're not doing any mapping here. We're just stitching together the 3D data. So you can imagine you can go through and start looking at what your glasshouse looks like from day to day. For instance, if you do this regularly and potentially look at the changes over time. You can also already use this to try and think about, you can maybe do size estimation or volume estimation, because although the 3D data is noisy and you can see this hopefully coming in, it's still of reasonable quality that you could start to think that you could deploy a system like this. Now I mentioned this idea of reprojection, and it's basically just taking the known motion, and you can see this idea over on the right-hand side. You take the known motion of your robot, your odometry, you take the masks that you had combined with the 3D information so you can predict where the new mask should be within your new image. And in this way, you're actually taking into account some of the spatial information of your environment while knowing how far your viewpoint, your robot has moved within the environment. So it's really taking into account both the depth and odometry information there. And this is by comparison to the previous system that I mentioned before. And you can use this idea to actually improve the output of your DNN, of your neural network. So you can do, for instance, better tracklet association. And that's the kind of idea you saw before. And just to show you, you can then go through and deploy this idea on a full field. And this is the example that you see here. So here what we're doing is we're deploying a hierarchical classifier again. We're doing detection of sweet pepper. And then there's a subclass classifier that allows us to say if it's red, green, or yellow, followed by the fact that we're also applying mask RCNN. So we're getting the per pixel segmentation of each instance. And what that means is if we then want to go through and manipulate the object or estimate the volume, we can. The system is also writing numbers per fruit, and those numbers are actually the overall surface area. Please keep in mind it's a 3D object and we're actually using the depth camera, so it is actually the surface or the viewable surface area that we're estimating there. And so you can see it goes through and detects the crop quite effectively, missing maybe one or two, but doing a really good job of what's coming through. Maybe the last point I'll make is you can see a number there in this particular video and the subsequent videos. Those numbers refer just to a unique ID. They're not referring to the count of the overall number of fruit. Okay, so we can go through and capture this for our 30 meters worth of glasshouse row and give the summary of that information in the end. Now I showed you this information and this summary for a glasshouse. We can also apply this not just in a horticultural setting, but also in an arable farming setting. So this is a video that you see of one of our systems within an arable farming setting, which is BondBot. So it's going through, and in this particular case, it's estimating where, and in this case in green is sugar beet. It's also estimating the area that they're taking up. So it's writing out the number, which is literally the area, I think this is in meters squared, to say where the crop is, how big it is, how much it's grown over time, and also then the other colors are going to be for the weeds. So now you can start to say, well, here's our crop, here's the state of our crop, here's the weeds, and we can decide how we want to interact with the weeds, because we're not just measuring the size of the crop, but also the size of the weeds. Please keep in mind here, this is also a fairly general classifier because it's hierarchical, similar to the case of sweet pepper. In this case, it's saying there's a plant, irrespective of if it's a crop or a weed. It's then saying within a hierarchy which particular weed species it is. So that means we can start to think about how to generally deploy this in different environments. And so when I talked before about the idea of doing things like weed scouting, you can start to see that one of the enabling factors for doing this is to have a system like the one I just described to you to say, here's the different plants, here's all the pixels of the different plants, go through and tell me what you want to do with all these different types of plants because they're potentially weeds. So this comes through and we're looking at a system and extending this not just to what kind of plants you have, but what's their state for a project called Weed AI, where we're looking at the efficacy or how effective a robot was for doing weeding both before and after. And in fact, any system, it doesn't matter if it's a robot or if it's just your favorite approach to doing weeding. Now, we are also building a robot to do precise weed management, and this robot is in fact BondBot 1. I'll try and introduce this relatively quickly because I think I'm running out of time. The idea behind BondBot is that we're trying to build it so it's got repeatable tools. And what you saw in the earlier video about AgBot 2 was the fact that we had repeated tools that were static. Okay, they were repeated, you could deploy them if it was over the weed, but if you had weeds in between the tools, you had to deploy multiple tools. So not very precise. If you have replicated moving tools, you can have different tools on each, for instance, linear system. And you can see those systems over here on the right-hand side. Or you can have multiple of the same, so you can deal with larger weed densities as you go through. Now, unfortunately, it's not just a simple matter of doing this kind of interaction. You also have to deal with the fact that you've got a complicated environment. And one of the things that complicates this environment in Europe is that when people do their seeding, they often don't do this using controlled traffic farming. Now, controlled traffic farming is where you GPS guide and plant within a row your system. And so we have to build up other systems like crop profiling that I'll talk about briefly to solve this. Now, in building up BondBot, we extended a simulation environment. So this is using the Thorvald, sold by Saga Robotics. We're also capturing near-infrared data. We're not going to have time to talk about any of this. You saw before sugar beet, but we're also applying this for corn and for other crop as well. Now, doing crop profiling, as I mentioned, is really important. And so we've built up BondBot 1, to actually go through and do this. And we do this based on very simple assumptions because we want to deploy it for multiple crops, being able to automatically find the start point. This is point number 1 of the crop rows, to be able to find them and follow them. Point number 2, to detect the end. And so we have a rear-facing camera that's symmetric with regards to the front-facing camera, so we can find the end of the rows to then switch to the new part of the row and follow that. And so some of the ideas for doing this, we're writing this up now for ICRA, so I can't go into too many details, but we're effectively trying to find the area of the crop where we've got quite dense and regular planting patterns, followed by usually fairly empty space in between. This is the idea of trying to find those peaks and troughs, responses to certain filters. And over here, you've got the idea of then trying to follow the center line, which is the crop row. We've been deploying this in the field, and you can see an example of this. We're deploying it not just for sugar beet on the right-hand side, but also beans and other crops as well. So we're deploying the system in the field. In this case, this is being deployed in Campus Klein-Altendorf. You can see the kind of fields that we deal with Phenerob. So this is one of the Phenerob fields. And what you can see here is that this system is automatically detecting the row, following it to the end. And then you're going to see within this video, it's going to detect with the back-facing camera, which is the one you can see at the moment. The end of the row is then automatically going to start switching to try and find the new starting point of the row. It's looking for features up here on the top left. It's going to have found the starting point for the new row and continue navigation down that particular row. Now, just to quickly round out the story, I mentioned that we're trying to exploit the temporal information. Obviously, we're not just using things like tracklet association or reprojection, we're also looking at temporal models. Now, one of the issues with deploying temporal models within areas like agriculture is that having sufficient data to train something like a recurrent neural network is quite challenging. So we have a paper that's just been accepted to the German Conference for Pattern Recognition, where we propose how you can generate virtual samples from that. You'll be able to find this on arXiv as well, where if you have a fairly static environment like we do in agriculture and you have non-motion forward, you can, from a single label image, go through, and we show this, generate multiple virtual samples to try and hallucinate this idea of having fully labeled temporal data. It's probably better that I take the time to let you go read that paper than talk in too much detail, except to say that within this table, what you see is that it provides a common boost for not just sweet pepper, so a horticultural setting, so BEP 20, with a higher number is better, but also for sugar beet, so SB 20, as you can see here. Deploying it for multiple environments is the key. I won't have time to talk about this video, but hopefully you've seen in summary that vision is a key for understanding the unstructured environment, and that if we start to really think about the information like the depth and the temporal information, we can do some really interesting things with being able to build up the models to show us where the crop is precisely per pixel to hopefully enable intelligent action. And the part that I didn't talk about was depth is also key for being able to enable intelligent action to actually interact with the crop. I think I've gone more than a little bit over time, so thank you very much for your patience. Are there any questions?